Okay, so we're going to do this in 45 minutes, which should be quite a challenge because we do have 87 slides to get through. So let's get started. My name is Momjian. It's great to be giving this talk. Jonathan is right. This QR code right here takes you to my website. There are 65 presentations on that website, 2,940 slides, 137 videos, and 770 blog entries about Postgres. So there's a lot of stuff there. I'm going to walk over here for a minute. So again, these slides and all the other slides are on the website, so you don't feel you need to have to maybe take pictures. I did do another AI talk. It's called Postgres and the Artificial Intelligence Landscape. It's more about discriminative AI, and I'm going to talk about that in a minute. But it talks about what's artificial intelligence, and mostly about machine learning, and then a database. But again, this was done before generative AI really burst on the scene, so it certainly makes sense that we have a new talk now to handle this. I'm getting a lot of feedback.
Yeah,
I wonder if we should.
We're trying to troubleshoot this. There's no way
Is it
Why
just,
yeah, why use the, yeah. If we turn that one off.
Yeah, sure. Oh, right. To turn it.
Here, hold on. There we go.
Here we go. Okay, let's try that.
Turn this one back on.
Okay, there we go. All right.
Yes.
Okay, so the outline of this talk we'll talk about how AI exploded onto the scene, particularly generative AI, the past couple of years. Then we're going to do a little math exercise with hyperdimensional arrays. You can't understand how AI works without understanding that. Then we'll talk about text embeddings, which will lead us to semantic and vector search. And that's obviously one use of AI for databases. Then we're going to talk about transformers and generative AI. And finally, explain Retrieval-Augmented Generation, another big use of databases and AI. And finally, talk about deployment and conclusions. What really drove me to write this talk was that obviously AI is super important, but it's hard to understand where a database really makes sense for AI. So you can't understand where a database makes sense for AI unless you actually understand what AI is doing. You have to understand the internals to understand where databases fit into that market. So what this talk effectively is a broad overview of AI technology, how it's deployed, how it works internally, and then section 8 is where we start to talk about where does the database make sense here and give you some specific examples. So again, a lot of the stuff I'm going to talk about is general to all AI, and then finally, toward the end, we'll talk about some really database-specific lessons of what AI is going to be useful for. Oops, sorry about that. Here we go. Great. So the AI explosion, I don't know how many of you realize how new AI really is in the market, but effectively November 30, 2022, so about pretty much 3 years ago, is when AI really burst onto the scene in a big way with people understanding it. That was ChatGPT-4. Effectively, the ability for computers to do human-like conversation was a dramatic change in what was available. And I'll talk about that a little more at the end, but again, this was sort of the watershed of where AI became a huge impetus in the IT industry. I also have a QR code here. It's like anything in blue. If you download the slide deck, you can click on anything in blue. And that blue is effectively a 6-video YouTube stream, which is probably 6 hours total. But a lot of the mathematics behind this and sort of understanding of how it works, I recommend that. We also have a URL here at the bottom. But again, all these slides are online, so it's easier to just click on them when you get there. So the two types of AI, effectively, up until 2022, most of the AI that we had, we thought of as discriminative AI. And effectively, discriminative AI was really involved with classification, things like fraudulent credit cards, image recognition, recommendations, prediction of trends, and language translation. Okay, so up until 2022, this is what people understood AI to be. But OpenAI basically revolutionized the public's perception of what was possible by releasing ChatGPT-4, as well as DALL-E, which is used to create images. So the concept is, instead of it making a decision or discriminating, we actually are creating new content. That's why it's called generative AI, because it's basically generating content. The previous discriminative AI wasn't able to do that, and again, we have OpenAI to really thank for this revolutionary change. So at generative AI uses, we have things like chatbots, which was big sort of in the early part of 2022, 2023. Then we have semantic and vector search. I'll be talking about that. Summarization, language translation, that's obviously super important. Ability to create images, video, and audio. And then also in software, we're seeing that now. Things like code creation, code analysis, data analysis, programming language conversion. I have some very big hopes for that one. And again, natural language interface, and I'll talk about this as we get forward. But again, this is the list that kind of set the world on fire for AI. Okay? So again, in general, discriminative AI, mostly supervised learning, requires training with known outcomes, often domain specific, and again, it's yield a prediction. Generative needs a lot more data, usually is more general, but it also is able to output new content, and that was revolutionary, of course. Okay? And again, just sort of a quote of the difference between the two. I like this image. This is discriminative. It's trying to distinguish between something like a dog and a cat, basically. Okay? It's not generating a dog or a cat. It's just identifying which is which. Whereas generative is generating new outcome. In this case, I'm showing you a graph of vectors. I'll be talking about that in a minute. But again, we're generating brand new content. Okay, any questions? So I take questions as I go. Okay, great. All right. So this is the hard part. This is the math part. There's no way to understand generative AI without the math. I was a math teacher, so I understand it, at least to some extent, but also to some extent, the types of things that generative AI is doing are really hard to concretely understand. And as you get through this section, you'll start to understand it. So let's talk about mathematics in general. Mathematics in general is really a set of concepts that allows you to represent certain physical quantities. Like, for example, the number of atoms in the universe, 10 to the 80. What does 10 to the 80 mean? How big is that number? I can't really understand what 10 to the 80 is, okay? That's a big number. But again, in mathematics, we can very easily represent it. Infinity, again, something that, like, you can never really see infinity by definition, right? But we have the concept in mathematics. And in fact, if you've ever done calculus, that is effectively the use of infinity. It means either an infinitely small slope against the graph, or the summation of an infinitely small number of segments to get the integral or the area underneath the curve. Okay? So again, we're using infinity here. We can't see infinity. We don't really conceptually understand it, but in mathematics we can represent it. Okay? There's a concept called duality, and the concept is that you can represent something either mathematically or computer-wise or physically, and they all kind of are the same. Like they really behave the same, and that's just, again, we have URL here if you're curious about sort of the philosophy behind this. So here's where we got to get complicated. Generative AI uses vectors of huge dimensions. So we live in a three-dimensional space, right? Length, width, height. A generative AI is typically in the 1,000 dimension or 10,000 dimension space. I can't understand what that is. I tried to represent 10 dimensions in this very crude graph. So we have 2 dimensions, right? Like X, right? And Y here, okay? But then at that point, we actually have another graph. And then at the point in that graph, we have another graph. And then at the point in that graph, we have another graph. And at that point in that graph, and that's 10 dimensions. Because each one is 2, there's 5 levels. All right? Now imagine instead of doing 10 dimensions, we're doing 1,000. Or 10,000. Hard to really conceptually understand what that is, but that's exactly what generative AI is doing. And there's no way to understand generative AI unless you can at least understand a little bit about what that space is. All right? So the range of each dimension is roughly a 4 byte floating number. So again, from 10 to the whatever, from, I think 4 byte is 10 to the 38 to minus 10 to the 38, something like that. So effectively, if you have 1,000 to 12,000 dimensions, that gives you a total range of points at 10 to the 9,000 to 10 to the 118,000. Now, how many atoms are there in the universe? 10 to the 80. So instead of, that's a big number. Now I'm looking at a number that's 10 to the 9,000 or 10 to 118,000. Just the scope of this, again, impossible to really understand, but that's exactly what's going on. And I'll sort of allude to it as we go forward about this sort of hyperdimensionality and why it's important, particularly when we start to talk about the training of how AI works, okay? So the way the system's set up is that you put these vectors in there, but the vectors are all the same length. So even though they point in different directions, they're all the same magnitude, as we call it, okay? Any questions? Yes, sir.
So when you say that each of the numbers is a 4 byte,
Right.
each of the axis is a 4 byte number, does that mean that the value in that axis is just like a number representation from whatever 0 to the max?
So the question is, when I'm talking about the 4 byte value in this slide right here, basically what we're saying is that the axis goes from minus infinity to infinity, basically. There are basically minus typically 10 to the, minus 10 to the 38th to 10 to the 38th. I think that's the range. Float 8's obviously a much bigger range, but I think that float 4 is only 10 to the 30, only 10 to the 38. But that's just one dimension, right? So that's that's a point on this line. So I have a float 4, and I got the same on this line, and then I got a ton of other dimensions. Okay. Other questions? Yes, sir.
So if each axis is 4 bytes and there's around 12,000 dimensions, does that mean that every concept is like 12,000 times 4 bytes in size?
That's a perfect point. The question is, if everything's 4 bytes, and yeah, actually, I don't want to do it, so this will be my backup. So if it's a 1,000 dimension array and everyone's 4 bytes, then that's a 4K vector, right? In terms of 4K bytes are necessary to store that vector. If I'm doing 1,000 dimensions, that would be 40K. Yeah, exactly what you're saying. Yeah. Other questions? There is some research in trying to use integers as well. I think DeepSeek is trying some anyway, there's some, it's not clear that we fully optimized it. This works, but it may be overkill. It may be overkill to do this. Again, we're only 3 years in. And I will tell you, this presentation took weeks of research, because what I realized was that everybody in AI understands one little part of their piece, okay? But to pull it all together into a unified presentation, like nobody's done that yet, and that's what this is an attempt to do. And again, I thank my employer, EB, they just kind of let me, I went to my boss, I'm like, I think I need to understand that. And we have a big AI product push in the company. He's like, yeah, you should go do that, And then 6 weeks later, out pops the presentation, and I've been delivering this pretty regularly for the past year, basically. First gave it in Brussels in January, and then been sort of giving it around. I'll be giving this in Armenia December. Yeah, so it's pretty much launched for a month. Yes.
Is there a way to like put this use in like a simple way for an idiot to understand? You know, like just like a way to just really like I understand like okay, there's like these just different dimensions, but like what's
Right.
like the practical? Is there a simple way to put that into like a practical use?
Yeah, I'm going to show you that in the next section. So the question is, yeah, the practical, I think the next section will help with that. Anything else? Okay. Oh, yeah. Mhm.
Yeah, in the mathematics world, they put n equals 0, 1, 2, the beginning.
Number of dimensions, yeah.
But in reality, you want to minimize, like a minimalist is better to, make things happen. So is there any opposite direction that you want to minimize that, so much dimension, so many dimensions into essential?
There are, so the question is, can you reduce the dimensions? As I get into generative AI, I'll show you that when you go to generative AI, we actually reduce the dimensionality of the computation because it's actually too expensive to do 1,000 dimensions. So you can pull them down quite a bit, yeah. Okay, let's go. All right, so training. This was a tough one. What really got me started with this talk, I was in Charlotte. They have Southeast Linux Fest in Charlotte every June. And not this year, but 2024, somebody gave an AI talk about semantic search. And at the end of the talk, I'm the kind of guy, like, I have a question, I'm going to find that speaker, I'm going to ask that question. I said, tell me, how do they make these vectors? Like where do they come from? Like, how do they, right? And because he was using vectors for semantic search, but I want to understand, where do these vectors come from? And his answer was, nobody knows. And I'm like, I think somebody knows. I think it just didn't come out of the sky. So I started digging in to understand how do these vectors get created, and that's what this section's about. But again, it took quite a bit of digging. So the way they do it is they create a vector for every word in the English language. There's about 30 to 50,000 words. Now that's very simplistic. There's other ways of doing it. You can do it in something called byte pairs, where each word is not a word, it's just 2 letters. And then you just have 2-letter pairs, vector for every 2-letter pair. I'm not going to get into that. We're just going to assume a vector per word. But again, in most cases, you're going to use 2-byte pairs for proper names and things like that. But again, we have a limited number of vectors we need to create here. Okay? And what they create these vectors, 30 to 50,000, and then they assign each vector a random direction in this 1,000 or 12,000 dimensional space. Now, what does that mean? We're in 3 dimensions, and our whole world lives in 3 dimensions. Okay? Imagine this glass has a 3-dimensional space, and we're going to add another 970 dimensions to this glass. Or another 10,000 dimensions to this glass. Okay? This space is so big that putting 30,000 or 50,000 vectors is nothing. There is so much space out here that they're just floating. That's why they can just do it randomly, because they're going to be so far from each other, it doesn't matter where we put them, is effectively the way they do it. Okay? And then they take a massive number of documents. I mean, like the whole internet level of documents. Like, forget just ingesting Wikipedia. We're going to ingest the whole internet into this. And then we're going to start crawling for other data we can find. Okay, so massive petabytes of data. And whatever beyond petabytes, I can't even remember what it is. Okay? And they run something called Word2Vec. Now, Word2Vec is actually developed by Google. Again, this is the original. We've got a bunch of URLs here. But what they do is they look at the word combinations, and they take every word, and they move it closer to other words that appear in the text. And again, they're digesting trillions of documents, okay? And for every document, they're breaking the document up into sections, and then they're moving the word closer to other words that happen to appear. All right? Or they move the surrounding words closer to the original word. There's two ways of doing it. There's some advantages of one over the other. I'm not going to get into it. Okay? So here's the classic example that is always used. It's man, woman, king, queen. And we're going to use this example pretty extensively. And again, what I've done is I put them randomly. Okay? So just random pointing anywhere. Now this is 2 dimensions. Let's pretend we're in 10,000 dimensions or 1,000 dimensions. And what I do is I take some text. The king is a tall man. That's a sentence. And I move the closer to the blue words, and I move king closer to the blue words in the second set. Is moves closer to those other words and all the way down. And once I'm done, I get another sentence. The king is a tall man, the queen is a beautiful woman. They sit together in the throne room of the castle. King gets closer to man, tall gets closer to man and king. Queen gets closer to woman, and so forth all the way down. Okay? And once I've done this too many times, I get this. What this basically means is that man and woman appear very frequently together in documents. And king and queen appear very together in documents. Okay? However, what's really interesting is if you take man and woman and you look at the angle between them, and you take that angle and you add it to king, you get queen. And that's the classic example. You might say this is ridiculous, it doesn't work this way. Remember, we're in a 1,000-dimensional space. Okay? So for example, if I move closer to this lady here, I'm moving farther away from my laptop. If I go this way, I'm getting farther away from her, I'm getting closer to my laptop, right? That's the way it kind of works, right? Now, if I'm in a 1,000-dimensional space, I can move closer to her in some dimension and not necessarily get farther away from my laptop. It's sort of like when I go up. If I could go up, I could kind of go up, and I'm not really getting farther away in the same, right? But again, we're 1,000 dimensions. So what happens effectively is if we've got 1,000 dimensions, there's probably one of those dimensions that represents royalty. And that particular dimension becomes very close for king and queen, but there's another dimension where man and woman are close, and they're close in that area as well. Does that make any sense? So I have, basically the way I think of it is we have like 1,000 attributes for every word. We aren't limited to just like one attribute or 2 attributes. But the other thing is this space is so big that even if we were limited to 1,000 attributes, there's a whole space of 10 to the 38th that we can move around in. So maybe the 17th dimension is royalty. But the 17th dimension may also be tastiness or color or something. Because again, we're in such a big space that even that particular dimension probably represents a whole bunch of things. Again, philosophically, I know it's hard to grasp, but because you're in so many dimensions, you can be moving things close to each other. There's some mathematics behind it. There's something called gradient descent, which has a tendency to identify which dimension is kind of the closest and triggers that one to move versus all the dimensions at once. So again, there's some mathematics behind it that's pretty cool. But this is effectively what's doing. And I told you I was going to explain the issue with the dimensions and how the training works. And that's exactly what I'm trying to do here. Okay? And this is basically just a stupid diagram of what text embeddings kind of looks like, right? Yes, ma'am.
Just going back to the previous
Yeah.
diagrams, is this like in the same dimension or like different dimensions? Because you have king, queen.
Okay, so the question is this in the same dimension or different dimensions? Honestly, I think this is in different dimensions. I hesitate to do 3 dimensions because I can't do it on a piece of paper, and then 4 dimensions would be just like.
So it's like 1 dimension per concept.
That's the way I think of it. 1 dimension per concept is the way I think of it. But again, because the single dimension is so large that there's probably some parts along that number line that represent royalty, and probably some other parts along the same line that represent color or softness or the Eiffel Tower, or you know what I'm saying? It's just crazy how big the space is. Other questions? Okay. So again, this is just something, this got an idea of how crazy this thing is. There are tools that let you look at the embeddings and actually study which dimension is actually close. I've never played with them, it sounds pretty cool. Yes?
There was a question there.
Oh, I'm sorry, yes, where was the question?
Right.
Oh, I'm,
Kind of behind the pool.
no, it's my fault, yes.
I had a couple, I guess, but I'll start with this. Like, a lot of words have the same word or two different meanings that are completely
Great
distinct.
point, yeah.
How does it handle that?
So the question is, a lot of words have two meanings, how does it handle that? You're gonna love this. One dimension probably represents one meaning of the word, and probably another dimension represents another meaning of the word. And that's historically been a big problem with full text search, because there's no context. But the way this works, effectively, you're using the word cat, let's say cat, okay? And the word cat in the question is close to a word like pet or animal or lick, okay? But if the word cat is closer to the word Linux or closer to the word Ethernet, in the question, all of a sudden it realizes, no, you don't mean the animal cat, you mean cat 5 or you mean cat, the Linux command, right? So effectively, these dimensions allow us to represent different meanings of the word. And historically, before generative AI, that was something we couldn't represent very easily. Okay. Other questions? Nobody behind the pole? We're good? Okay, good. All right. Okay, so let's get to our first application. And I love this one, semantic vector search. So what is semantic vector search? Postgres has had what we call full text search or phrase search since like the mid 2000s or even like 2003, I think. Amazing to have a full text search system in Postgres. But as somebody stated, those full text search cannot distinguish between, I think the classic case is, it's not cat, there's another animal that's the example. Anyway, it can't distinguish between those. But semantic search can, and it can understand that, for example, certain words are related, that again, full text search doesn't work. Now, full text search is really good typically for proper nouns like Germany or HP or Microsoft, like those kind of words. But when we start talking about normal non-pronouns, then semantic search, you can actually mix them together. But I'm going to show you some specific examples. So the way we can do semantic search, now that we've done the training, which took a huge amount of time, all right, what we're going to do is we're going to download a text embedding, or we may create our own. In this case, we're going to use the OpenAI one. We're going to choose the chunk size, be a sentence, paragraph, whatever, and then we're going to find all the text embedding vectors of all the words in the chunk, and we're going to average those, and we're going to store them in the database. So this is my storage phase. I'm going to basically create a bunch of vectors, right? It might be 1,000 dimensions for every word, every chunk, and each vector is an average of the words in the chunk. Okay, it isn't a word, it represents the average of the words in the chunk. Are we good with that? And again, we're talking 1,000 dimensions, so even if the chunk has a lot of words in it, the original sort of understanding of you know what I'm saying? Like you can average a 1,000-dimensional vector in a chunk size that has 1,000 words, you still can maintain a lot of the understanding of the original words. Okay, so to do a search, the way we're going to do that is we're going to find the text embedding vectors of all the words in the question, the query that they give us. We're going to do the same averaging, and then we're going to find the chunk who's closest to the average of the query. That makes sense, right? We took all our chunks, we averaged them, we stored them in the database. Now, we are going to effectively take those chunks and then we're going to do a query and average them. How are we going to do that? So, here's a setup. We're going to have 3 sentences. King's a tall man, queen's a beautiful woman. They sit together in the throne room of the castle. Okay, 6 vectors, 10 vectors. And then we're going to search for who is the king. All right, so we're going to install PG Vector. Everyone's excited who loves PG Vector. Again, we have some URLs down here. And also, the queries I'm using are actually in this SQL file. So if you want to run the queries I'm showing you, that's how you do it. Okay. So we create our table, we create our text embedding, and we effectively insert the 3 sentences, and then we create an index on it so we can get the closest, okay? And then we have a Python program, which effectively all it does is it takes our text, it averages the embedding for the string, and then inserts the embedding in the document. So this is where I'm creating my chunk storage, okay? And here's my table, here's my 3 sentences, and here's my chunks. Here's my vectors. Right? And these are the average vectors of these words. And again, they're all 4 bytes, which was the question of the gentleman over there. Okay? Then we're going to do a query. We're effectively going to take the query and we're going to average it right here. Where this is where we average the query that we've been given. Here's my search string. Okay? And now I'm going to say, give me the closest strings to that particular embedding, or that particular vector. Okay? So who is the king? Closest string is king's tall man. And here's my distances right here. Smaller is better. Who is tall? King wins, right? Great. We could have done this in full text search. Not hard. Okay? Who is short? King's a tall man. Whoa, what happened there? Well, the system knows that tall and short are related. So it is what it is, okay? Who is pretty? This is where we start getting impressive. Queen is a beautiful woman. Now, why did it know that? Because those pretty and beautiful are often represented together in text. So when we index pretty and beautiful, those are very close to each other in the text, and therefore the chunks ended up being close. Who is in the palace? I didn't say palace here, I said castle, right? It knows palace is near palace, is related to castle. It probably knows the palace is close to the throne room. Same thing, where is the chair? It probably knows that sit relates to chair, and throne room relates to chair. Throne relates to chair. So it probably knows that. Okay, that's why we're getting this example there. Okay, any questions?
But basically, that knowledge is external. It comes from something else. I mean,
In
the
this
knowledge
case-
that you are, the questions that you have, the answers are in the text. Okay, the 3-sentence text, and the question is which sentence of my 3 sentences is the best matching to my query.
Right.
But the other data that you're answering about the colors or the castle or the pretty and the beautiful, you need to get it from some external source
Right.
of data. Okay,
So what if you like, I didn't have time, but basically I'm using OpenAI's text embedding ADA02 model. So OpenAI did the training for me, and I'm connecting to OpenAI with a key to do this particular search. So I didn't do the training, they did it for me. Okay?
yeah.
Other question? Yeah, I'm sorry, yeah.
When you pick the dimensionality, that was based on OpenAI, is it almost always going to be based on an external library? Or?
The dimensionality typically is going to be controlled by whatever training dimensionality was used at the time. I'm sorry.
Does that lookup cost money
I'm sorry?
to connect those, to look up on OpenAI?
It costs money to use OpenAI, yeah. To use this embedding, I have to pay 2 cents or something. Yeah, it does cost money, yeah. Okay, let's go to transformers. So we're gonna we just did semantic search. Now we're gonna talk about generative AI, because I haven't shown you generative yet, right? I just showed you the semantic part, the search part. So we're gonna have to go pretty quick through this because I only have 10 minutes left.
Okay, do it. We'll go like 5 to 10 minutes over.
5 to 10 minutes over. Okay, so that would give me a little more time. I don't have to panic. Okay, so we're going to go through transformers. Transformers, again, just like WordDefect, this was invented by Google. I know, it's kind of funny. Google invents all this stuff, and OpenAI becomes the beneficiary. I'll explain why, I think, later on. But effectively, what happens is you take your query and you load something called an attention block with the text embedding of the words you used in your query. Right? We know what text embedding is now. Right? We're not averaging them now. We're going to create a vector for every word. We're going to adjust those, and we're going to go over and over again until we get our response. I know this sounds crazy. It shouldn't work, but I'm going to show you how it works. Okay, so let's walk through it. ChatGPT uses 96 attention blocks, and again, as the lady mentioned, it only uses 128 dimensions. So it brings dimensions down because this is very compute intensive and it works just fine at lower dimensionality, okay? And again, we're making this kind of simple. But this is the diagram I wanted to show you. So here's our text embeddings, right? The ones that were trained with petabytes of data, okay? And we pull, here's our sentence. What's the capital France? What is the capital France? And for each word, we put the vector in that slot, okay? And this is our query, okay? And what we do is we adjust this vector to be closer to this vector. So that's the first stage. Then we have these two vectors closer to this vector. And then we have these three closer to that vector. And then we do that for the of and France and the question mark. Again, this is kind of silly, but you get the idea. Every vector is getting moved. Okay? So now we have what. The second vector is not what anymore, it's what is, because it's what and is close to each other. What is the is now the third slot. What is the capital of the fourth slot? So forth all the way down. Okay? And then each vector is basically continually moved closer as we go through these computations. So now what is moved closer to what is moved closer to what is the, and we run it again. Okay? So what stays the same, what is the second slot, what is and what is the is the third slot, what is the, and what is the capital is the fourth slot, all the way down. This is our second attention block. Third attention block. Fourth attention block. We're going to do this 96 times. Okay?
Is that why you have so many slides?
That's why I'm saying this. That would be hilarious. That would be hilarious. All right, so what's really weird, after you run all the attention blocks, the last word, the last vector, okay, we go back to the text embedding and we say, I've got a vector, tell me the closest word that matches that embedding. And that's the word you reply to the user with. If you've ever used ChatGPT and you type a question, you know the words kind of come out one at a time. That's not an effect. Effectively, that's the way, because it's computing those attention blocks over to generate the next word, the next word, the next word. Okay. And then to get the second word, you basically do it again. Okay. And then that word is your second word that comes out. And you basically just keep running this machine, and it just spits out words. Now, this is very simplistic. It doesn't talk about sentence structure. It doesn't talk about a whole bunch of stuff. But the concept I wanted to get you across is that basically it's using the text embeddings, it's making them closer to each other, and the final embedding, the final vector, they then look up what's this close to, and then that's the answer to the question. Okay? So let's walk through an example here with ChatGPT to give you an idea. What is the capital of France? The capital of France is Paris. How did that work? How did you get Paris? Because remember, we took capital and Paris, and we're mixing them together, right? And remember I showed you queen and king and man and woman. So in some level, when you take capital and France together, you end up pointing to Paris. Because that's the way the training went. It knows city and Paris are mentioned a lot. It knows that capital and Paris are mentioned a lot. And it knows that France and Paris are mentioned a lot. So again, this is all part of that process. Okay, where's the capital of France? I phrased it differently, didn't matter. Where's Paris? It gives me a whole example of what's in Paris. Okay? This is interesting. Columbus is in Ohio, where's Paris? Now, I've adjusted the vector a little bit with these preview, this first sentence. And it's a little unclear here. It says Paris is in France, but it also mentions a Paris in Texas. So it's not quite clear that it's pointing to Paris here. It's kind of hedging its bets. And then if I say I live in Texas, where is Paris? Then it goes whole hog, right? Now we're talking about Texas. In Texas and in Paris. Where is it located? Blah, 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 near Dallas. And then it talks about, Paris, France. And then it's back to Texas again. And anyway, I guess refer to things, for global tracks, the Eiffel Tower replica and a cowboy hat, whatever. It kind of goes back and forth trying to give me an answer because I've given it kind of, the vector's a little funny. Okay? Any questions? Yeah.
Do you need words like is? Like, could you just say like where Paris?
So the question is, do you need these noise words? I've never tested it. I don't know. There is a sense that it learns sentence structure because it does repeat. It does give me real sentences. I don't know the answer to that. Other questions?
I've got a question.
Yeah.
As you probably know, when you're using one of these tools, it's subject to a context limit.
Yeah.
Where it gives up or sometimes visibly degrades. Can you relate that to what you were saying about attention?
Yeah. So in fact, the question is context limit. Context limit originally in this in generative AI when it came out was about 1,000 words. Now they've gotten up to like a megabyte or 1,000. Maybe it was 4,000 bytes, I think, or 10,000 bytes, and now it's up to a megabyte. So they've been increasing what we call the memory or the context of how much you can remember. So what you see people a lot doing is taking these humongous documents and just sort of throwing it at ChatGPT and saying, summarize this, or you know what I mean? Like, so you're absolutely right. There is a limit to how big this thing is, but they've been increasing the limits a lot. Yeah. Yes, sir. I know there's a question over here, though. Yeah.
A couple of questions. One, but if you keep asking the same question, it's not deterministic, right? So you get different answers, even though we've been talking about like trying the closest vector. So I guess that's one thing. Another one also just typos and something. And you mentioned like if you type something in broken English, it seems to figure out. I don't know if that's a coincidence or whatnot, but you're going through all these permutations. There are people that say like, let me do pigeon English, or let me do like typos and everything.
Right.
So I'm curious.
So there's certain the reason you get random answers is there's a randomness in this calculation of vectors. So sometimes it'll pick a vector that's not necessarily the closest one, and you can even tune how much randomness there is. I don't remember, there's some science behind why you need some randomness. That's why you get different answers. In terms of broken English, yeah, it kind of figures it out. Like it's just really looking at the vectors. It doesn't understand a lot about the sentence structure in a lot of ways. There's one other question over here. Yes, sir.
The slide you had with it had text on it, and it had a sentence as part of the answer. As if you're talking about a different such and so.
Yeah, it is right here.
Yeah, that one. Does there have to be sentences in the training body that say that, or?
No, absolutely. The question is, do I have to have sentences that exactly match that? No. What happens is, it's just looking that Paris, the word Paris, remember we talked to the gentleman about cat, to have different meanings. Well, Paris is close to Texas, and it's close to France.
Right.
And when I'm saying I live in Texas, where's Paris, it has a tendency to favor the dimension of the word Paris that's near Texas, and less emphasis on the dimension of Paris that's closest to France. Yes?
Apologies if I missed this, but do we know like the reason, or like how did someone come up with like, oh, if we do this attention blockchain thing, this might work? Like, was that just like a coincidence?
So the question is, how did this happen? I'll go into that toward the end.
Sure.
Okay. All right, let's keep going. All right, so retrieval-augmented generation. I'm going to have to stop. I'm sorry. Retrieval-augmented generation is basically a way of boosting the usefulness of AI by prefixing the data with some information. So, for example, if I say, where is Paris? Obviously, it talks about Paris. But if I say reply, if I prefix it or reply briefly, it actually shortens it up. And it actually looks like this. It actually has a special payload, which is called a system role. And that's the part where you sort of prefix this. So, for example, I can prefix where is Paris with I live in Ohio, Columbus is in Ohio. I get a different answer. Again, prefix it with Texas. I get a different answer. I can also do prefixing of JSON, which gets kind of crazy. So here what I'm doing is I'm prefixing some orders to a question. So the same every question is going to be prefixed with this JSON. All right? So I said, when were the orders made? The system, OpenAI is able to understand the JSON, the structure, and is actually able to output my orders with my order ID and date. if I say where is the earliest invoice, it knows which invoice is actually the earliest one, which is right here. Okay? I can ask for the total of all invoices, it can total it for me. I can ask for the average invoice amount, it can do that for me. I can ask for which, with 30-day payment expected, which invoices are overdue. It can give me the overdue date for my invoices. It can find me the total of invoices that are not pencils, which is cool. I can even say, what is the next expected order date? It looks at the days between the invoices to try and predict when the next order will happen. So this is really powerful, right? I mean, again, you're using RAG, you're prefixing with some information, but it's pretty cool. You can also generate SQL queries. So I'm saying, give me a query to get the latest invoice date. And that's a valid query for what I'm doing. I can even use Postgres, and I can just prefix it with a JSON query that's actually converting all my invoices for a specific customer into JSON. And now when I ask for my invoices, it actually knows the answer. So again, this is an example of dynamically using RAG to prefix a query with some information that might help the generative AI give a useful answer to the question. Again, just proof of concept, but it's kind of cool what can be done. Any questions? Okay, so let's get this to the last section. I like this slide because it basically brings everything together. Here is our vectors pointing in random directions. That's how we started our training, remember? Okay. And once we went through the training data, we got text embeddings with vectors pointing in training directions. Okay. And then here we're using semantic search to generate some chunks, and we can store those chunks here, and we can generate semantic queries. We can query the vectors and get the nearest chunks. And down here we have RAG. We're using generative queries. We're running through that normal cycle, and then we're generating output text. Okay. This slide is, I think, the best slide in the presentation, because what it does is to summarize everything we just learned and tell you, based on what we know now, when is a database useful in AI and when is it not useful. So for example, text embedding vector training, batch changes, mostly static data, huge data volumes, probably not something you're going to do with a relational database. Doesn't make sense. Okay? Semantic vector search, search existing database context. That's a good one. Okay? Number 5 and 6, transformers, generative AI. No. Way too much computation. You don't need transactions. You don't just do it somewhere else. Okay? Retrieval-Augmented Generation, add details to user queries. That's good. Language queries or retrieve data. That's good as well. Generate SQL queries. I got a link down here. That's kind of cool. If we can make it so people can naturally language say their queries, and then they get their answers instead of having somebody write SQL. That's cool, right? And finally, at the bottom, this is a new technology, Model Context Protocol. How many people have heard of MCP? Anybody? Oh, wow. Okay. I've been asleep at the wheel then, because I've just really looked at it in the past couple months. So it's about a year old. It effectively is an interface, an open interface to allow AI models to access external data. Now that could be performing an action, but it could also be getting data from a query. So you basically create a spec, you write what the module does in natural language, in English, and then the system will use that to answer questions. Or to get more data, so if you want to do a web search, you want to look at Git commits, you want to look at the weather, these are modules that have a standard API that allows these generative models to basically pull data from external sources. Okay, so that's also a really good one for databases. I don't even cover it here. It's kind of out there. It's hard to explain in this example. Okay, in terms of deployments, again, we can use a cloud model where we're getting our embeddings from somewhere else. We can use self-managed. We can go to Meta. We can go to Hugging Face, which has a whole bunch of models. We can train them ourselves. Again, I'm not going to go into this. Feel free to download the slides or look at the URLs here in the description. There's a lot here. It's just too much to go over. There are a bunch of Postgres AI solutions. that are available, again, at all different levels. Sometimes it's tuning, sometimes it's applications, sometimes it is query generation. Again, different options for AI at different levels. Okay? And any questions? Oh, yes, sir.
This is probably too big for right now, but LLMs are usually pretty bad at time.
Yes.
Historically have been.
I'm sorry, LLMs are bad at time.
Time, like bad at like temporal reasoning, I guess, is in my experience. A lot of people say that. Is there a reason that doesn't like particularly fit well into like the dimensional understanding?
So why does time not fit in well dimensional? I think part of the problem is you train it with a whole bunch of static data, but there's no dynamism to the data, it's just static. So the concept of changes over time, again, it gets into data without really understanding when that data was created. And I think it just doesn't have enough context to really understand what it's reading. And we'll probably fix that by starting to maybe identify the date of the ingestion. But it's hard to represent a time ingestion information into a vector. That's really the problem. That we're moving words around as close to each other, but there's no context of in this year these two words meant these things, and in another year they meant something else. And it was, you know what I'm saying? It's just not. It doesn't have a time dimension to it really. That's probably why. Yeah.
When generating those attention blocks, right? When doing it the first time, the second time, do they have to recalculate the first one again when you're doing the second one?
So the question is, they have to recalculate the attention blocks. There are some optimizations. Once you get through the 96 and you get your first word, you don't have to go through all 96 again. You only have to kind of worry about the last word and just kind of work on that one. So you actually don't have to redo the whole thing. For every word that come out, there are definitely some optimizations related to that. Yeah. Yeah.
I want to ask you about a question about like deploy about vector database. Let's say if I am Wikipedia, I want all my chunk be embedding, but ChatGPT released maybe ChatGPT 6, but my model is embedding in ChatGPT 5. Does that mean I need to re-embedding with a new model?
Okay, so the question is, if embeddings change, you have to use the same embedding every place. So if your embedding the embedding you use for chunk storage and the embedding you use for query has to be the exact same embedding. Okay? And the same thing with generative search. As soon as that embedding changes, you gotta redo everything. Yeah.
So is this sharing anyone want to address it? Because we know all model is evolving very quick. So if we do check.
Yeah, that's an unsolved problem. We'll put it that way. Let me just get to the conclusion here again. We're kind of in a very infant period. Again, I want to give Google credit. Word2Vec 2013, attention blocks Google 2017, 2022 ChatGPT comes in. How did Google miss the boat? They effectively were so focused on their core search and advertising, they didn't understand the value of doing this, and I think they also were worried that doing this would cannibalize their search, and it actually has to some extent. But again, now they're behind the ball and they're trying to catch up. They had a lot of stumbles at the beginning. It seems like maybe they got their footing back. But again, very interesting how they led. But again, we're not the innovators here. Okay. I want to finish with two quotes. They are contradictory, but they're also both true. The first quote is from 2023. A year ago, if you had said to me, in our lifetime, we will have capabilities like we have now. If you explain the kind of things that ChatGPT can do, I probably would have said, I don't know if we'll have those capabilities in our lifetime, and now we have it. So the speed with which this is moving is staggering. Very true. The second one is also true. We are used to the idea that people or entities that can express themselves or manipulate language are smart, but that is not true. You can manipulate language and not be smart, and that's basically what LLMs are demonstrating. So I'll finish with one quote. I was at Riga. We had a Postgres AI seminar, and we were talking about hallucination. People have heard that term before. And effectively, I said, some people are saying, well, how can it hallucinate sometimes and not other times? The bottom line is AI is always hallucinating. There's nothing different when it gives you a hallucination and it gives you the right answer. It is you who decide when it's hallucinating or not. Okay? So it isn't like there's some flaw that makes it hallucinate. It's hallucinating all the time. Sometimes the output makes sense, sometimes the output doesn't make sense.
You're absolutely right.
But it's not, there's not a sense that it somehow understood the ones it said right and like got bopped on the head for the ones it got wrong. It is hallucinating all the time. So thank you very much. I apologize you went 9 minutes over. But thank you.
I think in fairness, we started about 9 minutes late, so maybe it was on time. All right, well, thank you, everyone. I believe we're playing our next one in January, right? So in January, so have a happy end of the year, and we'll see you soon. Thank you. Thank you.